Okay, guys, this next one is we're going to try and solve for K. Remember, we learned that there were a couple of ways to solve for delta G, three ways, delta H minus T delta S. And then we're going to use the equation delta G equals negative RT.
Negative RT ln K.
Natural log of K. And so we're going to use that equation to solve this problem.
Mm-hmm.
So, in this particular problem, we know that delta G is what?
Negative 33.3 kilojoules per mole.
Negative 33.3 kilojoules per mole. That looks like a circle, doesn't it, instead of a triangle?
Okay. Shape thing turned back
I think I must have turned it back on. Okay, so now what you're going to do is that delta G, now here's something important, is negative 33 kilojoules per mole.
Right.
Now we've got to convert that to joules per
right.
mole. There's 1 kilojoule is 1,000 joules. Now you'll see why I need to do that. I can do that without a calculator.
Yep.
That would be negative 33,000.
It's actually 33.3.
Oh, 33,300 joules per mole. Now why do I do that? Because if you recall R, that's the gas law constant, is 8.3145 joules per Kelvin mole. So I must have like units. I could have converted R into kilojoules. I just find that a little bit cumbersome. So negative 33,300 is equal to negative, because it's negative RT, 8.3145. I won't put the units on here. And the temperature at this, I didn't see
25 Celsius,
so that's
it says.
298 Kelvin, right? Just add 273 to that. Times the natural log of K. Okay, now, what you would need to do mathematically, this could be done with a solver, but I think we're going to teach you how to do it without a solver.
Yeah, just do it with the math.
So we're going to divide both sides by negative 8.3145 and 298, right?
Yep.
So negative 8.3145 and 298. Of course, they cancel on this side. And what do you get, Mr. Sands,
you
divide
get
these numbers?
13.4.
13.4. The negative signs, negative divided by negative gives you positive,
Yep.
is equal to the natural log of K. Now, how do you find K in this particular equation? You'll take
the inverse of natural log, which most calculators hit the second button, then you hit the ln button, and it's the little e function.
So e to the log of something is the something. In this case, e to the log of k is k.
Right.
So I'm going to take e to the 13.4 power. And you get?
686,780. We'll do 686,780.
780. Now, sig fig wise, what have we got here?
It's like 3 sig figs.
I think we're going to go with 3 sig digs there. So that'll be 68,700.
Yep.
So 68,700.
Nope. Sorry. 687,000. 687,000.
Oh, I didn't do that right.
Yeah. Sorry. I told you wrong too.
687,000.
Yep.
There we go. So 687,000. Now that's a K.
And equilibrium Ks do not have units. We don't worry about
no
them.
units on that, right. Now, that's a big number, Mr. Simmons.
That's a huge number.
So when you have an equilibrium constant that's very big, what does that mean?
It means it favors the product side extremely.
Remember, equilibrium shifting to the right.
Yes.
And I would have actually predicted that this would have a very high equilibrium constant. Why? Because I had a delta G, which was negative.
Spontaneous.
And whenever you have a negative delta G, you will have a very high value of K.
Yeah, because it's...
Or at least a positive K.
Yeah. Yeah.
Or a number bigger than 1, I should
and
say.
it makes sense because the spontaneous reaction is going to favor the products.
And so that's how we do this. All right, now we're back to the PowerPoint. Let's jump now here. Calculate the value of delta G for the following reaction at 390 K, et cetera, et cetera, et cetera. So here's the problem. So how are we going to tackle this one, Mr.
Well, we've got some concentrations here, and we want to find delta G. So if I know concentrations,
you can find.
We should be able to find K, products over reactants.
Yeah. So we're in this problem.
Are we assuming
folks,
we're at equilibrium here?
Yeah.
I think we kind of have to. Otherwise, we're going to do
we
Q.
have to be at equilibrium.
Yeah.
So we'll add that to the paper, I think.
Yep.
Okay. So what we've got is the reaction is into. This is the classic reaction. Plus 3H2 makes 2NH3. And it's at equilibrium, so we have 2 molar ammonia, so this is 2 molar. And the hydrogen is 1.25 molar. And the ammonia, no, the nitrogen
3.01.
3.01. So the equilibrium constant, the K expression, would be the concentration of the ammonia.
Squared.
Why do you need to square it?
Because the two coefficients.
Yes. This is a K. Remember how we did Ks? Let's like KC from chapter 3 over the concentration of the nitrogen.
Chapter 3?
Chapter 3. Chapter 13.
There we go.
I knew. I was just checking on you. Make sure you got the answer. And then you'd cube that right there.
Yep.
So now we actually just plug in some numbers. In H3 is 2.0, and we're going to square that. I know that's 4. If you 2 squared is a 4, divided by 3.01.
That was kind of fun.
Times 1.25, and then you ask cube it. And Mr. Sams is Mr. Calculator boy.
Mr. Sams just made a mistake again.
And he has to do it again because he's slow on calculator. He must make a mistake all the time.
Syntax error.
Syntax error? I thought you were smart.
I left out a parenthesis. No.
4 over 3.
This is not my day. There we go. 0.68.
0.68. All right, so that's K, folks.
That's K.
And our equation was delta G equals negative n RT natural log of K. So,
NRT?
not nRT, negative RT. I was thinking PV equals nRT, and I was getting very crazy on myself. And of course, R is 8.3145. Was our temperature 298?
Temperature
389.
389 in this one.
All right. 389 times the natural log of 0.68.
Yep.
And when you get your calculator
you
out,
get 1202.
1202. And the units on that does have units. That'll be kilojoules.
Yep.
Per mole. Now, it's positive,
It is
right?
positive.
Even with the negative sign here, right?
Yep.
So that means that this one would not be spontaneous.
And that makes sense because it's a small K. K is less than 1, so it's going to favor the reactant side.
Makes sense. I want you to add this somewhere. This is really the delta G equation. Delta G, hello, what happened there? Let me redo that. Delta G equals delta G naught plus RT natural log of K. Now, what's true when delta G equals 0, Mr. Sams?
Delta G equals 0, we're at equilibrium.
So when you're at equilibrium, actually this should be Q.
Q.
I'm going to get my things right here. Actually, let me erase so it's easier to see. We've got this cool erase feature right now. We like this. Okay, if that's equal to 0, then you'd say delta G naught plus RT, natural log of K, because now you are at equilibrium. Right. So if you resolve this equation, delta G naught is equal to negative RT, natural log of K. So that's where that equation comes from that is important. There's this important equation, but this is the equation that it comes from.
Yeah.
And then, of course, while we're at it, delta G is also delta H minus T delta S, right?
And we can find it with products minus reactants.
Also, you can say delta G, is the sum of the products from the back of your book, PROD, minus the sum of the reactants, etc. So we just want to make sure, actually, while we're at it, there's delta G equals negative NF E naught.
Yep.
And that's, we're going to learn about that one. This is in chapter 17, which is actually our next chapter.
So I love electrochemistry.
I do too, because electrochemistry is so cool because you can make batteries. And we can talk about how my dad's propeller in his boat corroded because he did not have a sacrificial anode.
Oh, sacrificial anodes.
The old sacrificial anode problem.
Yeah.
Well, I hope you are learning much in your science land so that you can be a happy chemistry person. Hello, my name is Bill. I don't know. Bill!
Oh no, Mr. Bill!
Mr. Bill, yes, I was thinking of Mr. Bill.
You guys are way too young to know Mr. Bill.
You should do a Google search
That's Saturday
on
Night
Mr.
Live from the
Bill.
80s.
From the 80s when Mr. Bergmann was a younger lad. And you weren't even thought of, probably. Okay.
I was probably in middle school.
You were in middle school in the 80s?
Yeah.
I was in college. 82 to 86.
Oh, 82.
College.
I was only 5 years old in 82.
Oh, you are so young. 82, I go college. College boy in 1982. Yes, indeed. Yeah. Oregon State University. What college did you go, Mr. Sams?
I went to Biola University.
Biola. That's a little private one, isn't it?
It is.
Yeah. Now, don't get that confused with, like, Ohio State. I went to Oregon State, the Beavs. Okay. Well, we hope you guys are having a grand time. And now you know which colleges we went to. How's that for fun? We'll talk to you later. Bye.